So we're going to continue talking about a work power. Yes, last time was power, and now we're going to look more at, shall we say, the energy. Kind of come back to energy a little bit again as we continue working forward. There are a couple terms that we do need to be introduced to again. It is a couple, it's just more of an idea is that you have conservative and non-conservative forces. As the term itself suggests, a conservative force conserves as it goes, it doesn't change, such as gravity. Non-conservative forces change over time. They change the force that's being given, and therefore you have, say, one such as friction. So when we talk about early on, we say, does running a 400 or walking in a circle, do you do any work? Well, that's going under, when we said that no work was done, that was under the impression that the work being done is in a conservative force kind of bubble where friction is non-existent. But to walk, we need to have friction. Therefore, it is a non-conservative force. So is work done? Yes. But a lot of times we try to eliminate, simplify it by saying, you know what, let's not deal with friction, because it complicates things. Although we know in the real world that it kind of just getting rid of friction isn't really something that can happen. So in the picture here we have kind of three different scenarios where we have work done by gravity on a closed path, lifting an object off the floor and kind of lifting it up and around. And then you have work done by friction on a closed path, meaning a box is then being moved around on a floor. And then the last one, that's just a craziness of things, but work done by a conservative force and a zero doesn't on any closed path. It doesn't matter. As long as we kind of indicate that it's a conservative force, meaning friction is being omitted or eliminated. As long as friction is being eliminated, we can say that it's a conservative force, making some of the calculations a little easier, as opposed to a non-conservative force, meaning we will have to take friction into account. And so work will have to be done with friction being there, because you do have to overcome that force over time or over a certain distance. And so that will, and it even as we would know and suspect, it would increase even the amount of force required, therefore the amount of work required over a distance. Kind of a very simple little table here. What is a conservative force? Which ones can be considered to be conservative forces? And which other ones can we not? Pretty much gravity, elastic energy, because usually a purely elastic energy would allow for it to be transformed. Electric energy, friction and air resistance and friction are almost tied the two together. Tension's going to have friction because you're going to have it's just going to have a interaction. Propulsion, pushing or pulling, are non-conservative. And ultimately, what we get down to it, the nuts and bolts of it, is only things that are considered to be potential energy can be defined as conservative. So potential energy is our true and only conservative force. And it is this potential energy that we have. And I think it's easy for people to understand gravity is a potential energy. When you hold something up, it's going to fall. It has the potential to fall. Elastic, pull a rubber band. You're trying to release said energy. The electric one is the one that gets sometimes. It's a potential. It has the potential to do work. That's what is stored in the electrical lines. You're like, but it's electricity. No, you have the potential to do work. You plug in something into a power line, it then now has the ability to finally do work. Charge a phone. Run a refrigerator. It's a potential energy. When we look at the non-conservative forces, and they're like, why is it so difficult to kind of define and kind of figure out some things? Any push or pull by a person is non-conservative. That in itself all of a sudden just like adds a lot of variability into things that when we're trying to figure some things out, and why when you're like, well, when I pull on this, why does it not do what it's supposed to do? It's a non-conservative force. Sometimes we're thinking that it is conservative force, but even though it's not. Tension, you have to have, almost any, look at this, you're like, oh, well, anything that's moving that has mass pretty much is going to add some things to it. Why was it nice in some of the forces stuff early on where we would say, ignore the mass of the string or the rope because it just adds a dimension to things. And that comes into play. So once something's moving, things get complicated. So if we just all don't move, maybe life will be simpler. But if we don't move, nothing gets done. Our familiar examples of potential energy. Stretching an elastic band. Those really super good, awesome rubber bands that you pull back. A lot of energy in there. Harder it is to pull back, the more energy you put in to pull it, more she goes. An object at some height above the ground. Gravitational potential energy. and the potential energy with it stored within chemical bonds. That chemical potential energy. Why do you need to eat? Because of the chemical potential energy that is stored there. And that's usually kind of that's a topic usually done at the end of chemistry classes, usually, or end of one semester, beginning of another semester, so to speak, in college. Your thermochemistry. Gravitational potential energy. Usually we use the symbol of U. Capital U. I've also seen gravitational potential energy written as GPE, and even shortened up as just PE, based on, you should know what we're talking about. Whether it's gravitational potential energy or electrical potential energy, a lot of times I've seen PE as the thing that is end up being used. The H, or the height, that's your delta Y. Of subtracting them out. Let's try it out. An 82 kilogram mountain climber is in the final stage of ascent of a 4,301 climb of Pikes Peak. What is the change in gravitational potential energy as the climber gains the last 100 meters of the climb? Let the U, or gravitational potential energy, equal 0 at sea level. Because that's technically how mountains are measured, based off of their height above sea level. So again, two ways to do this. So I'm going to resize this a little bit. So that we have it. The one way is we need to find the difference in potential energy. So we will have the UF, which will be the total height, which would be the mass times gravity times H, or again, H can be Y. Okay? And so therefore we would put those items in. So 82 point kilograms, gravity 9.81. We have the total height of Pikes Peak at 4,301 meters. We need to find and put that into our handy dandy calculator. And we get a value of, I think that's what, 3,459,810.42 joules. We now also need to find the U, that's a U, not a very good, well-written U. the initial, and again, we're looking in the last 100 meters. So the mass times gravity times height. Mass is still 82 kilograms. Gravity, still 9.81. And since we're in the last 100 meters, or before the last 100 meters, it'd be 4,201 meters on there. So we then put that into our handy dandy calculator. And we find that we get a value of 3,379,368.42 joules, and not the bling bling kind. Now, to find the difference in that, final minus the initial. So we then take our values that we found and subtract them. And we then find that we got a value of I believe 80,442 joules, and not the bling bling kind. So the easier way takes into account the fact that we're just gaining and in a way where you can kind of do the change in height in itself, because the mass and the gravity don't change. So we'll just have the U is equal to mass times gravity times H. And so we have 82 kilograms times 9.81 times 100 meters. And we get a value of 80,442 joules. And so we have that.